Okay, good afternoon, everybody. Hey, welcome to another video by Papa Lim Physics Classroom. Okay, today we'll be looking through one of the Sec 4 normal acad paper by Queenstown Secondary School. Okay, it's 2021 paper. Okay, now same as before. If you have not see the paper before, okay, I have left a soft copy in the Google Drive. Okay, the link to my Google Drive is in the description panel panel below. Okay, feel free to go and click and just take a look at the paper. Okay, and if you have done your revision, and I will say that this paper is a good paper for you to actually test out your revision to see how much actually you have understand and what are the gaps in your learning. Okay, now without delaying, okay, we'll look at the paper Queenstown Secondary School 2021. Okay, prelim paper for 4NA. Now, so for those who have done it, okay, the answer are here. You might want to pause the video, okay, to check your answer to see which questions do you make mistakes, whether it's a careless mistake or is it a conceptual misunderstanding. All right, now, once you have done your marking your assessment, okay, now let's look at the questions in detail. Same as before, if you need certain question, okay, feel free to drag the video to the respective timing so that you actually get the relevant updates, understandings or explanations for that particular question. Now, for question 1 and question 2. Question 1 and question 2, I will not dwell too much because, for example, like in question 1, the idea of micrometer screw gauge, the basic principles of using micrometer screw gauge is actually one of the key essential skills that the students have to know. Okay, you have forgotten about it. Okay, I actually have made a video in the chapter 1 under the micrometer screw gauge whereby I talk about how the zero errors and how to read the micrometer screw gauge and also the vernier caliper. So if you have not revised that particular section, okay, I have leave the link to the video in the description panel below and also on the top right hand side corner of your video. Okay, the link is up there. Okay, you can actually take a look at that the link there. Now, so once you have revised on the usage of micrometer screw gauge, you will find that actually question 1 and question 2 actually is quite easy. Okay, it's in fact quite basic, I would say. Okay, scalar and vector for question 2. Which of the following include scalars? Which of the following are vectors? And the good thing about this question is that the options given are quite, I would say, it's quite standard. Okay, scalars. Okay, temperature, energies, all these are scalar. Okay. Now the other examples of scalars that we commonly use, okay, in other paper, I would say it would be density. Scalar, or one of the commonly used scalar is density. Okay. Of course, we have the usual suspect, the distance, speed. Okay, all these are scalar. Okay, after that you have time. Time is one of them when you talk about scalar. Okay. As for vectors, I would say the usual suspect for vectors would be like velocity, acceleration, force. Okay, all these are the usual quantities that you see for examples of vectors. Now, for question 3, okay, you have a distant time graph. Okay, a distant time graph. I remember a distant time graph. Okay, if it's velocity time graph, yes, the area under it will be, the area below it will be actually equivalent to what we call your distance traveled. Okay, remember it's velocity time graph. In this case, the question given is actually distance time graph. Okay, so note the differences. Okay, once you notice the differences, you will straight away actually you can narrow down onto the references to shaded area. Okay, shaded area is distance. This only makes sense if the graph that you are looking for is actually velocity time graph. Okay, velocity time graph, the area under the graph is actually a distance traveled. Okay, but not distance time graph. So note the differences. Now, as for question 4, okay, constant speed. This same is one of the favorite clues that I always tell students. The moment you see constant speed, it's one of the favorite clues. Why? Because constant speed is quite a common term or common clues that we give to students, because constant speed actually give the information that the acceleration of the object is actually 0 meter per second squared. Okay, and true enough, okay, you take a look, if you look at 0 meter per second square, that's the first clue that is given to us. And other than that, there's actually other meaning. Okay, From constant speed, we can deduce that the acceleration is actually 0. And from acceleration equal to 0, I can make another deduction. Okay, whereby if you look at Newton's second law, F net equal to ma. If acceleration is 0, you'll find that we can actually conclude that F net is equal to 0 when A is equal to 0. Okay, so this is what we mean by the different layers of inference that we can get actually just from a simple clue such as constant speed. Okay, now when we talk about constant speed, the forces acting on it, I would say that I will not be able to conclude that every situation will imply equal force acting on the object. For example, one of the common representation or one of the common working that we see will be like the force applied. Okay, it might minus the friction equal to 0, and from there you'll find that the friction will be equal to the force applied. This will be the one of the common working that we see. But of course, it doesn't mean that in this case it means that the two forces are equal. In this case, equal, but it doesn't mean that it is always the case. It's just one of the possible scenario. So that's why when we talk about there are equal forces acting on the object, this statement actually implies is true and only true. Okay, it's always true. Okay, but in fact that this particular scenario is only true for certain assumptions or certain scenario. So that's why this statement is actually wrong. Okay, it's not always true. Okay, and no forces acting on the object, which is wrong because why? It is no resultant force acting on the object. I can have ample of forces, many forces acting on an object, but if the resultant force, the net force of all these forces is 0, okay, it is still a possible one. And from there, I can that's what we mean by acceleration equal to 0. Okay, because I will be able to deduce that the net force acting on the object will be actually 0. That's why my answer here will be D. Now, question 5 here, we look at the mass and volume. Okay. Now we look at which is floating and sinking, so which is on top below. Okay, I will say that straight away, the moment I have mass and density, you will know that it will be a test of understanding in terms of density. Density formula is mass divided by volume. Okay, mass divided by volume. Okay, so what you do is you actually calculate the density of the object, density of each of the liquid. So if you have density X, okay, you calculate mass divided by volume, you'll be able to get the density of each of the object. So from there, we'll be able to decide whether the object float or sink. Okay, so density Y and density Z. Ultimately, what you're trying to do is after you found out their densities, what you're going to do is you're going to make use of the differences in densities. Okay, whereby you look at the lower density. Okay, will actually float. Okay, the biggest or the highest density will actually sink. So this is the perspective that they are looking at. So once you actually identify or when you calculated the distance, the density, okay, you will be able to deduce that who is on top, who is below, because the top side has to be the lightest, and after that the bottom side has to be the highest density. Okay, and with that you should be able to narrow down your answer to be option A. Okay, based on the density in the table that you work out with. Okay, so you need to work out the density first, then after you can deduce the location of the three liquid in the tall cylinder based on the fact that the higher density and the more it sink. Question 6. Okay, you look at the moments. Okay, there are 3 rods. Okay, there are 3 forces acting on the object. A moment question. Okay, now when we look at moments, right, the common thing that we look at moments, okay, by various forces, we are actually looking at using principle of moments, whereby we look at the anti-clockwise moment, okay, equal to the clockwise moment. So what you're looking at, you actually need a series of like a set of to identify where are the clockwise moment, where are the clockwise moment, where are the anti-clockwise moment. So for example, if you look at what I always tell students is actually to consolidate, okay, what are the possible to have a systematic way of consolidating the forces and their respective moments. For example, okay, let's look at the table. So here I will say, I will actually identify what are the forces, perpendicular distance, and actually the moments. Okay, for example, for first, there are 3 forces here, 1 Newton, 2 Newton, followed by 5.5 Newton. Okay, so these are the 3 forces. So for each of the forces, what I do is I always identify their respective perpendicular distance. For example, for first 1 Newton, the perpendicular distance will be actually be from the pivot, from the force to the pivot, which is actually this particular distance, which is 1.3 meter. So I will place the distance here, 1.3 meter. Okay, then after that, for 5.5 Newton, the perpendicular distance will be 0.6. So I'll write 0.6 meter here. Perpendicular distance for 2 Newton will be this D here, like given in the question. So it will be D meter. So what I do now is once I have the force and this perpendicular distance, what I do is I will identify what are the direction of moments of turning. For example, if you look at the 1 Newton, okay, the 1 Newton is pointing downwards. With respect to the pivot, actually the 1 Newton is actually a clockwise moment. I would say you'll generate a clockwise moment, okay, controlled by, I will label it as M1. Same thing, okay, if it's 2 Newton, the arrow is downwards, okay, if you pull the pivot with respect to the pivot, okay, the arrow downwards for 2 Newton, the force 2 Newton will actually generate a clockwise moment, okay, so this will be clockwise moment, I'll label it as M2, okay. Now, as for 5.5 on the other end of the rod, okay, of the pivot, it is still pointing downwards, but with respect to the pivot, the force 5.5 Newton actually generate a anti-clockwise moment, okay, which I will label it as anti-clockwise moment M5.5. Okay. Now, so what we do now is after we identify all the forces and all the respective moment, what we do is we'll use the clockwise moment, we'll use the anti-clockwise moment equal to clockwise moment, principle of moments, anti-clockwise, which is equal to the clockwise moment. So what I do now at the next step, okay, is actually group all the clockwise together and group all the anti-clockwise together. So for clockwise, I actually have 2 sets. Okay, these 2 sets here, I'll actually group them on the right side. Okay, which is M1 plus M2. Anti-clockwise, I have 1 set, which is M5.5. So this guy will be here. Okay, after that, what you do is substitute all the variable inside. So M5.5 consists of 5.5 multiplied by 0.6 meter. M1 will consist of 1 Newton multiplied by 1.3 meter. Then after that, M2 actually will be 2 Newton multiplied by D, which is the perpendicular distance. And from there, you can actually work out D, which is a simple algebra, and you'll be able to work out what is the value of D. And the value of D, what we have here will be C. Okay, C will be 1 meter here, 1.0 meter. Okay, so take note of how I work out the questions. I would say the way I do moments, I always encourage students to actually identify what are the forces and what are the perpendicular distance, the respective perpendicular distance, and from there actually branch out to actually identify what is the direction of moments and what are the factors or what is the formula or what the equations for that particular moments. Okay, so and after that, what you do once you finish these 3 steps, okay, you actually use principle of moments, okay, to actually guide them together, because most of the time it's actually a balanced system, and with balanced system it will mean that the clockwise moment, it will be equal to the anti-clockwise moment. Question 7, the CG of the object. Okay, CG. Now CG will be the center of mass, whereby is the shape whereby is the point whereby all the masses in the body are equally distributed. For example, for the position 1, the CG will be like I would say at the center of the center, like the represented by the dotted line. When we say it's the center, it doesn't mean it's half of it. It doesn't mean half. Okay, when we say the CG is at the particular position, we are saying that the top side of the mass is actually balanced out with the bottom side of the mass. Okay, means the center of mass, in terms of center of gravity or center of mass, center of gravity is the point whereby both masses are actually the same, evenly distributed. So now what happens is for picture 2, when the hand is being raised upwards, okay, means the mass of the hand is actually on the upper side of the body. So you'll find that this section here this section here is actually this mass. If I use the CG at the same place here, if I use the CG at the same place, okay, you will find that there is an additional portion of hand there, which is the mass of the hand, which will actually render the upper part body at this position to be actually greater than the bottom part of the body. So for, as I mentioned, CG is a half, is actually whereby the mass of the object is actually balanced. So to balance the height, I would say that because of the raise, he raised hand, the CG automatically actually increased a bit. Yeah, so you'll find that actually position 2, because of the hand is being raised, the CG is actually higher than position 1. And from here, we can deduce that high CG is actually a bad cause. Okay, because high CG make you more unstable. And what happens is when you bend over, okay, you'll find that if I still continue G at this position, you'll find that this small mass here, okay, confirm, okay, will not be the same as the bottom side. So what we do is, for the mass to be equally distributed, I would say the center of mass will be somewhere around here. Okay, so from here, we will say that the project of the mass, okay, is equivalent to the distribution of mass is equivalent to the center of gravity at this position. So which means we can say that the center of gravity, the top side of the body, is actually balanced by the bottom side of the body. So that's why, and that's why we can identify the CG to be along this line. Okay, and also the fact that, okay, position 3 is actually the most stable position because it has the lowest CG. Okay, given that all the 3 areas actually they have the same base area lah. So that's why C is correct. Now for this question here, it will be I would say it needs the students to actually use the formula for power, which is actually power is equal to energy divided by time. Okay, first thing first, okay, when you look at power, I will look at power, okay, or to calculate power, you'll find that the variable needed, you need energy and time. Okay, and you'll find that for energy and time, one thing to take note is always remember time has to be in seconds. And so the unit for time has to be seconds. So check. Oh, is the unit of time in seconds? Yes, check. So with that, you can actually take the values, let's say energy and the time taken, and actually substitute straight away into the equation to calculate the power of the students, producers. Okay, so for this to be the least power, okay, for this to be the least power, which of the students produce the least power? Okay, you'll find that least power, for power to be small, you'll find that the energy, the numerator has to be low. Okay, and the time taken has to be large, where to be more. Okay, if you look at it in terms of the formula. So the students with the least energy with the largest amount of time will actually have the lowest power, which is A. Okay, 1,200 joules. Okay, time taken is 10 seconds. Now, which of the row describe solid and gas at a constant temperature? Okay, at a particular temperature, what will happen? Okay, this will be the, I would say, the property of state of matter. Okay, example will be a solid has definite shape, definite volume. Okay, so the moment you see this, you actually know the answer already. For solid, one of the main property about solid is that solid definitely has definite shape and definite volume. And once you identify this particular case, you'll find, B is the only one with solid, definite shape, definite volume. So with that, I can actually conclude B is actually the answer. Okay, so you need to know what are your facts, what are the facts, what are the factors include in each of the section, each of the topic, so that you can actually identify what the question is asking. Okay, at which topic the question is asking at a very fast rate. Now, which of the surfaces is the best absorber and best emitter? Okay, so remember, first thing first, best absorber, best emitter. Most of us should know and must know is that the best emitter and best transmitter will have to be black. Okay, and it has to be dull. Okay, and the surface area has to be big. Okay, so these are the 3 factors that we actually look at it. Okay, dull, black, and big. Okay, then after you look at your surface area, maybe big is surface area. Then after you look at your temperature differences. These are the 4 factors that will affect the readings. Okay, that will affect the heat loss. Okay, so which of these is the best absorber? Okay, best absorber, best emitter. Okay, means I'm looking for dull, black, big, and maybe hot temperature. So here we only got the color and the texture. So it will be dull black. Okay. And the best emitter will also be the same. It will be dull black also. So answer will be C. Now we look at question 11. Okay. What happened to a open beaker? So here we look at is open beaker. Open beaker. This is where the boiling take place. Okay, so in the beaker, when the boiling take place, basically what they are saying that when boiling take place means there is actually a change in state. Now, when there's a change in state, if you look at the thermal property, the property of the liquid, okay, if the particular state, the liquid is actually boiling, it means there's a change in state. Okay, it's boiling means there's a change in state currently. What will actually happen is definitely the molecular force, the intermolecular force, okay, the intermolecular distance, okay, the intermolecular distance will actually be increased because the intermolecular force actually is weakened. Okay, and as such, the molecules, the distance between the molecule actually increases. But what happens is because your boiling occur, or whatever energy are absorbed in boiling is actually used to do what? It's actually used to change state. This potential energy uses the energy to change state. So what you have now is because the energy is given to change state, which is your intermolecular bond, which is your potential energy. Okay, so as a result, little or no energy is actually given to the kinetic energy. So when no kinetic energy is given, you will find that actually the average velocity of that liquid actually remains the same. Okay, so take note of the understanding, okay, whereby you can actually craft out these sentences in terms of wording, in terms of like exam question and section B, or in this case, it can also be a section A question. Okay, now when water evaporates, some molecule escapes. Okay, this remember when we talk about molecule, when we talk about evaporation, we're looking at the surface of the liquid, and the energetic liquid actually differs. Okay, then after that, the weaker molecules at home actually, then after will be left. The weaker molecule, the weaker kinetic energy in the liquid will actually be left behind, and after that, the temperature of the liquid will actually reduce. Okay, so what will happen is when the energetic molecules actually escape, what is left behind is what the molecule at the surface, okay, will have be lower kinetic energy. It has to be at the surface because at the most, evaporation only occur at the surface only. Okay, so what will actually happen? Okay, so if the question asks for what has left in the beaker, okay, then this A will be the answer. Okay, but the question is the question asked is what happened to the molecule that escaped. Okay, not is what happened to the molecule that's left over. Okay, the molecule that escaped, it will be actually the molecules, the layer of molecules which have actually higher kinetic energy as compared to the rest. Okay, and thus, okay, you need to know what are the general properties of different states and what are the respective properties when you look at different states. Okay, when you look at transfer of thermal energy, and also you pack it together with your thermal property. Okay. Now, question 13 will be on EM wave. Okay, which of the electromagnetics travel faster in outer space? Outer space here means vacuum. The moment you hear outer space, straight away, you know what wave travel in outer space? Only one of them, which is a transverse wave. Okay, so this is where we end. So the moment you know is outer space, okay, you will know that it's vacuum. So you know it's talking about transverse wave. Okay, and you know a transverse wave, it will be actually talking about gamma, infrared, or ultraviolet, visible light, etc., etc., etc. Okay, and one property between EM wave or transverse wave is actually when they travel in vacuum, the speed actually remains, they are all the same, which is 3 times 10 about 8 meters per second in vacuum. Okay, so take note of the properties of the EM waves. Okay, remember in EM wave, when you look at EM waves or the transverse wave, one of the common properties is that they are able to travel in vacuum. And the other property that we always closely monitor is actually the magnitude of the speed itself. The transverse wave, when you talk about their speed in vacuum, all of them actually has the same speed. Okay, whether it's microwave, ultraviolet, they all have the same speed, which is 3 times 10 meters per second. Displacement time graph, displacement distance graph, sorry. Same as before, displacement distance graph for displacement for displacement time graph, displacement distance graph, same thing every time before I read the question, but the moment I see the graph, I will tell myself, I'll highlight to myself what is the wavelength, okay? And after that, what does the distance represent? This is represent one cycle. So it is one cycle here. It actually gives you 0.4 meter, which is actually what we call the lambda, which is the wavelength. Okay, and so given that the wave, the frequency of the wave is 15 hertz, the wavelength is actually 0.4 meter. Okay, then after that, what are the second thing that you need to take note is actually the amplitude. The amplitude is from the middle line, the equilibrium, all the way up to the crest, or sometimes we say from the equilibrium all the way to the trough. Okay, so you should be having displacement 10 cm. Okay, 10 cm here. What is the wavelength? 0.4 meter, which is actually 40 cm. So the answer here will be C. Okay, so take note of like small tricks that we ask for it, like conversion, all these small tricks. Also remember how to what you need to do when you look at units where we are like SI units. Okay, so be alert a bit. 15. Okay, transverse and longitudinal. Like I mentioned before, the moment you ask for longitudinal, there's only one wave in the syllabus, which is sound. Anything related to the sound is of confirmed plus gravity chop is a longitudinal wave. So whether it's ultrasound, infrasound, and sound, it's definitely a longitudinal wave. Okay, so take note of it. And with this, we actually look for example. We are done for example 15. And for example 15, one thing to take note is the use of the fact your light wave. Okay, your light sometimes we tend to get mixed up between light wave, radio wave, or we thought radio wave is sound wave. Okay, so, or sound waves they tend to be longitudinal. Okay, but it's not actually. Radio wave is part of the transverse EM spectrum. Now, number 16, which of the effect on sound heard by the man when the frequency of the sound changes from 600 to 6 kilohertz. Okay, so we talk about these changes in your frequency. When you change frequency, the most obvious impact will be actually the change in your pitches. So this one straight away you know is a change in pitch. Get from 600 to 6,000, wow, it's definitely high pitch. So you will actually go for higher in pitch. Now the cliff question, okay, what happened when a man stands in front of the cliff and clap his hand once? Okay, echo. Here we look at echo, whereby actually the sound actually travels from the man all the way to the wall. Then after that, from the man to the wall. Then after that, hit the wall and come back here again. So the distance traveled for this wave is actually twice the distance apart. So which means this will be 500 meter. This will be 500 meter. Okay, so in total, you are looking at actually a travel of 1 kilometer. Okay, and you given that the speed of the sound is actually 330 meter per second, which means it will be 1,000. Okay, it will be 1,000. Okay, distance divided by time and the time taken, okay, which we are unknown. Okay, let's take a look here. Hey, what am I writing? Okay, so the distance traveled here will be 1,000 meter. Okay, so given that the speed is 330, so if you look at the time, it will be 1,000 divided by 330. Now, take note, this is the time taken it takes to travel to and fro, or aka the time taken for the echo for the sound to travel to and fro and come back to the system. Okay, so if you look at the calculation, you will find that the answer will actually be given will be actually 3.30 seconds. Okay, so take note of this. Okay, quantities measured in voltage. 18, I will not dwell too much. I will say quite straightforward. Question 19, same thing. EM charges. Okay, you look at EM charges. in the sense that if I want the formula for current, the basic formula, the one that we always use, okay, it will be I equal to Q over T. Okay, and charges, so we look at number of charges, is actually 600 Coulomb divided by time will be 4 seconds. So after that, you will get the respective answer out, which it happens to be C, okay, 150. Okay. Okay, then after that, same thing. The last one is whereby the reason I actually recorded in series, there are results connected in series, then in parallel. Okay, so if voltmeter 1 read 8 volts. Okay, so if I know that the total is 15, I know one stretch is 8. Okay, so the remaining here will be actually 3 volts. Hey, sorry, it will be 15 volts. 7 volts, sorry. 7 volts. Okay, because why? Because this section, the potential difference here, V1 plus V2 has to be the same, what we call the values. Okay, to be the same answer as above. So what happened is, what is the reading in the voltmeter? Straight away, so you know one is 8, total is 15, because the EMF here we are looking at is the EMF, which is the total voltage, is equivalent to the V1 plus V2. So 15 volts, V1 is 8 volts plus, okay, V2. So 15 minus 8, it will be 7. So straight away, you know that V2 will be 7, and that will be the answer for this particular question. Okay, so with that, we come actually to the end of the MCQ. Okay, so and we will move on to your paper 2. Okay, now let's look at paper 2. Okay, now paper 2, the first question, sorry for the misprint, but I would say it will be an easy question, whereby the question actually the marker actually want us to give the corresponding quantity, okay, with respect to the units. For example, if I give you Newton, so the student is supposedly to write down what quantity is the unit referring to, or this thing, etc., etc. So I would say it's quite easy lah. Now the second question will be on the dumper truck. Okay, dumper truck is on the travel over soft and sandy ground. Okay, it has white tire. White tire. Okay, white tire. Now explain why the white tire actually allows the truck to travel across the ground without sinking. So now what happens is the white tire. What does white means? Okay, the clue about white here refer to actually what I call a large, okay, contact area. Okay, large contact area. Or sometimes I actually like to call it to be large perpendicular area, perpendicular contact area. Okay, to be more precise. Okay, so when we talk about, contact area. So contact area here. Okay, so the keyword here we are looking at is perpendicular contact area. Okay, so what we are looking at, so when you say contact area here, what does it imply to? Is actually we are referring to the concept known as pressure. Why pressure? Because pressure talk about the force being distributed over my contact area. Okay, so when you look at explanations, is that when it start off with white area, so white tire, the first thing we talk about white tire here is actually to hint to students to actually look at the contact area. So the first clue the first keyword that we actually need students to write is actually to comment about the contact area, which is here, okay, contact area or perpendicular areas, and thus, okay, same thing is I will encourage students to actually write the phrasing. If you don't write the formula, you can actually replace this with the word since, okay, pressure is force per unit area. Okay, this will actually replace this word here. So let's say I can replace this word. So if you don't want to write the formula, you can use force per unit area. You can actually replace this statement here. Okay, so what you do is you use this statement, force per unit area. Okay, try to mention this so that you actually inform marker to tell the marker that actually you know what pressure means and what are the variables involved. After that, you comment on the size of the pressure, because with a larger contact area, the pressure on the ground actually decreases, and because you decrease, you are less likely to sink. So the keywords that we are looking for, actually, you look at the keywords, there are actually 3 sets of keywords. First is contact area. First is the contact area. Second is to highlight to the marker that actually you are using the concept of pressure, followed by the idea that the pressure on the ground actually decreases. Okay, so when we look at explanation, we actually look at your formula to serve us as a guide, to actually tell us what are the keywords that you're supposed to write down. Okay, so like a systematic guide like that. Okay, then after that, same thing. Pressure exerted. Okay, the sixth wheel. Okay, the weight of the force, the weight is 5 Newton. You have 6 wheel. Okay, so the total area. So you have so with pressure and the forces, you actually can calculate the total area of each tire. So this is the total area. So you have 6 tires, that's why you divide by 6. And after that, remember, leave your answer in 3SF. Okay, that will be the contact area we are referring to. Okay, so I would say it's not difficult here. I would say the slightly difficult one would be maybe getting the right keywords to explain part A. Okay, so that will be more important. Calculation at part B is actually quite straightforward. Okay, but of course, take note of the fact that you need to divide by 6 because of the question mentioned 6 wheelers. Excuse me. Now, for question 3, the hawker pushes a basket of durian. Okay, for question 3, right, we are looking at is that the hawker is pushing the durian across a certain distance. Okay, so the question asks for work done. So work done, one of the main thing that we are looking at, remember, is that the force and distance has to be in the same direction. So you look at the picture here, is the force is moving to the right side, 240. Okay, so the distance move in the same direction or in the same axis as the force would be this horizontal, which is 5 meter. So work done will be simply of 240 times 5 lah. Okay, so 240 times 5, you will get you'll be able to get the work done, okay, by the hawker, okay, which is 1,200 joules. Okay. Okay, so after work done, what the question asked for in part B is when they take 90 seconds, what is the power? Same as before, like I mentioned, power is work done. Work divided by time, okay, work per unit time. Now, one of the common trick that we always like to use is actually we will make sure the time is in like minutes or hour. So just have a habit of whenever I give you time, okay, to make sure that the unit of that particular the unit of time, okay, is in second. Okay, that is the most important thing. Okay, so if it's 5 minutes or 2 minutes or 1 minute, make sure you convert it to seconds, okay, before you substitute into the equation. Okay, because whether it's 5 minutes or 300 seconds, it actually makes a big difference in the calculations. Okay, and good enough. Okay, the question now is they actually give you 90 seconds to push the basket from the lorry to the store. Okay, after that, you get the answer to be 13.3 watts. Okay, that's the power exerted by the hawker. Then that will be end of the first question, question 3. Okay, then after that, we look at question 4. Question 4 is on EM spectrum, okay, whereby quite interestingly, they give you, as usual, they give you the EM, the component wave of the EM spectrum. But what is interesting here is actually they even includes the wavelength. Okay, now here take note is when we look at wavelength, especially for microwave, electromagnetic wave, all these waves, remember the use of prefixes. Okay, whereby we look at your units. Okay, so take note of the prefixes. Okay, whether it's micro or -10, or I have a -6 and a micro here. So take note of the users of the prefixes. Okay, so that you need to be aware of how to convert the prefixes. Okay, in your chapter 1, how to convert the unit with prefixes to actually standard SI units. Okay, because you usually prefer to substitute the value in terms of the SI unit into the formula so that we can get all the correct unit at the end of the day. Now, mixing wave A and B, I would say it's quite easy. Okay, if you know the arrangement of the waves in terms of wavelength, you should be able to identify it as visible light, X-ray and visible light. Users of ultraviolet, okay, same thing. I will not dwell too much. Most of you would have known. Okay, remember for EM wave, the most the component that we're looking at when you look at the revision is actually to understand the arrangement of EM waves and actually to look at the pro and cons or the uses of your EM waves. Okay, now calculate the frequency of infrared. Where is infrared? Infrared, okay, is 100 micrometer. Okay, 100 micrometer, like the workings are suggested 100 micrometer. Remember to convert it to SI unit first. So it's 100 times 10 power minus 6. Okay, micro is minus 6. Speed of the speed of EM wave. Speed of EM wave, two constants that students are required to know is actually the speed of the EM wave in vacuum, which is 3 times 10 to the power 8 meter per second. The other constant that we need to know is will be the gravitational field strength on Earth, which is 10 Newton per kg. Okay, so these are the constants that we would like to know, would like to remember. So for this formula, we use V equal F lambda. Okay, lambda is, like I mentioned, is 100 times 10 to the power minus 6. Okay, speed is 3 times 10 to the power 8. So if you look into if you substitute this number into the equations, you do your algebra, you will get the frequency of the infrared, which is 3 times 10 to the power 12 hertz. Okay. Now for section B here, same as before. Section B, the moment you see section B, okay, please remember, okay, section B, you are supposed to answer 2 questions. So remember to choose or to read all the 3 questions first before you actually attempt any question. Because you need to choose the 2 questions that actually allows you to score the most mark in this section. Okay, because having the maximum to grab the most marks in this section actually will value add. Okay, will actually help to push up your grades in your overall paper. Okay, now for first question will be a kinematics question, okay, whereby he has a story whereby he travels constant acceleration until he reached 45 meters per second at the initial. After that, he maintained constant speed for the next 10 seconds. Okay, after he slow down and he come to rest at 5 seconds. Now, based on information, they ask you to draw the graph. Okay, so based on this, you will find that the graph will be quite easy. I would say the first 15 seconds is 45. Okay, I would say it's roughly here. 1, 2, 3, 4, 5 will be here. After that, he maintained 10 seconds, 45 meters per second for next 10 seconds. So for the next 10 seconds and 25, it will be here. After that, for the last 5 seconds, he will actually decelerate or brake uniformly. After that, for the next 5 seconds until he hit rest. At rest, remember rest, okay, means the speed is 0. So these are the coordinates that you have. So with that, actually, you look at you take a ruler, you connect all the points, you will get actually a nice shape. If I'm not wrong, it should be a trapezium shape. Okay, so this is the line you're talking about. Okay, so if you complete the graph based on the story, okay, then after that, you actually get this. Okay, connect the, okay, so this will be the shape that the question is referring to. Okay, so first cut for, I would say the 3 marks, I would say it's quite easily. Okay, all you need to do is actually convert whatever information is given in terms of in English, okay, in terms of story, and after that convert it into a graph value. Same thing, kinematics, okay, speed time graph, like I mentioned in other papers. Okay, first thing you do at kinematics after you are ready, okay, take note of the unit, especially time. Okay, make sure the time is, take note of the unit at the time axis. If it's in minutes, okay, remember most of the time, if it's minutes or hour, most likely you need to convert that number into seconds. Okay, because if you speed time graph, if it's in meter per second, most likely the time, okay, you need to be in second. Because later on, if we calculate distance, which is area under the graph, you need to make sure that the x-axis, your time, is in seconds. Okay, so first thing, please check where the axis, okay, of the time. Second thing, like I mentioned also, again, okay, take note, the gradient is the acceleration. The gradient of the graph actually denotes the acceleration of the object. Same thing, the area here, where I mentioned the area here, will denote the distance traveled, okay, by the object, okay, by the motorcyclist. Okay, so take note of the 2 factors, which is the standard approach. Okay, so take note of them. So once you know them, especially once you take note of these 3 factors, okay, x-axis, time, the unit, gradient, which is the acceleration, the area under the graph, which is distance, you will find that, okay, now you are ready to actually tackle the questions for this part B for this question. Okay, so part B, explain or define average speed. Okay, it's a standard answer here. Okay, so I will not dwell too much. Most of which should be actually well versed with it, which is actually total distance divided per unit time. Okay, calculate the average speed for the first 15 seconds. Average speed, remember, average speed, the formula is total distance divided by total time. Okay, total distance divided by total time. Total time given already is in the first 5 seconds. Okay, but what happened to the total distance here? Total distance, remember, for the first 15 seconds, or to be exact, for total distance is actually referring to the area under the graph. And based on the question, give me a minute. Let me use this color first. Okay, so first 15 seconds, okay, until here, distance traveled will be actually what we know as the area under the graph. So effectively, what I need to do is actually I need to find the area of this triangle, which is half. Your base will be 15, the height will be 45. Yeah, half base times height. So this is where I get my formula, half base times height. I'm actually trying to calculate the area of the graph, which is the distance traveled. Once I have the number 337.5, okay, then after that you divide by the first 15 seconds, you will find the speed of the object to be 22.5 meters per second. After that, we will look at deceleration in the last 5 seconds. Last 5 seconds. Remember deceleration. Okay, now take note of this. This is the problem with most working. Okay, try not to do this working. Okay, we always like to, I just replace the negative sign, or instead of final minus initial, I'll just replace it with deceleration. Just reverse the minus. Okay, then after I get the answer for deceleration straight away. Try not to use this approach. Okay, try not to use this approach. Okay, so what we always do is we go back to basic. Okay, we know the acceleration formula. Acceleration formula is actually final minus initial divided by time. For the last 5 seconds, you look at the last 5 seconds, the final speed we are looking at, final speed, this guy is actually 0 meter per second. Initial speed for the last 5 seconds, for 25th second, the initial speed here we are looking at is actually 45 meter per second. So if the initial speed is 0, so which means it will mean that the v is 0, initial speed is u, which is 45. Last 5 seconds means the time taken will be 5 seconds. It will bring us to negative 45 divided by 5. It will bring us to negative 9 meter per second squared. Or to be exact, 2SF. Okay. Negative 9 meter per second squared. So what we do is negative 9 meter per second squared actually refer to acceleration. Acceleration negative implies one thing. It will implies, okay, your answer don't end here because the question asking for what? The question asking for acceleration. You are looking at deceleration. You are only at acceleration only. So if I know that the acceleration is negative 9 meter, 0.0 meter per second squared, indirectly I'm actually referring to the fact that the deceleration of the object of the motorcyclist is actually 9.0 meter per second squared. Okay, same answer. Okay, remember acceleration is negative 9. Okay, deceleration is 9 meter per second squared. Okay, it's the reverse. Although, okay, you take note, if you look at the mathematics, okay, A is negative 9, okay, then deceleration is positive 9. There's a difference in minus sign. So some of us, we will tend to say, hey, since there's negative sign at the end of the day, can I actually substitute the negative sign back into the equations? Actually, then after that, what I do is I would use deceleration formula. I will have a deceleration formula which encompass initial speed minus final speed divided by time. Now, I will say try to avoid this this pattern because you're looking at it in terms of math. Math, I would say, is okay. But when you talk about acceleration, you're looking at it in terms of physics. We are looking at it in terms of concept. And when we talk about change in velocity, we are actually looking at final minus initial, the difference between the final and the initial speed. So that's why it will not make sense if you just throw in the negative sign and after it become change in velocity become final, initial minus final. So it will not make sense actually. So that's why I always encourage students to actually go back to the basic, okay, the formula. After that, start from basic. After that, work your way up. And if you look at the formula, if you look at the steps that you need to do versus the alternative, okay, this one. Okay, the steps, I will not say they are actually just as long. Okay, you will not actually save any steps. Okay, but going back to basic actually helped me to actually reinforce my understanding. Calculate the kinetic energy. Okay, calculate the kinetic energy of the motorcyclist at constant speed. Speed given is 45 meters per second. Constant speed. Okay, so half mv squared, I should be able to get the answer straight away. Okay, quite easily done. I will not say this is a hurdle. Now, the last question here. Is it last question? Oh, no, sorry. It's not last question. Okay, second last question. Okay, no, second last question. Circuits. Okay, you have circuit, you have actually two light bulbs in parallel. Okay, these two light bulbs in parallel, identical light bulb. Okay, and after that, you have a 5 ohm resistor in series. Given that this is 0.7 amp, the current flowing in the first upper light bulb is 0.7 amp. First thing first, take note, if it's 0.7 amp at the top branch, we will be able to deduce that the current, okay, at ammeter 1 at the bottom side, okay, will actually be the same number. Okay, why is it so? It's because the fact that they are two identical light bulbs. Two identical light bulb means the specifications and the experience will actually be the same. So if the first light bulb actually experiences 0.7 amp, the second light bulb will also experience the same thing. So straight away, you actually will know that actually for the light bulb, the upper branch and lower branch, okay, upper light bulb and lower light bulb, the current actually is the same, 0.7 and 0.7. And with that, we actually can work out, we can deduce something else. So if the top branch is 0.7, the bottom branch is 0.7, I will actually know that the current going through the light bulb, going through the 5 amp resistor, I call this I total. Automatically, I actually know indirectly, I will know that I total is consists of 0.7 plus 0.7, which is 1.4 amp. So even without reading the question, I actually can deduce that the current coming out from the battery is actually 1.4 ampere. Then after that, when it hits the nodes, when it hits the parallel branch, the current is actually split equally up and down. Okay. Defined current, okay, I will not dwell too much. It's I would say everybody should know and must know. Okay, current is defined as the rate of change, rate of flow of charges across a particular component. Okay, deduce the ammeter, like I mentioned before, deduce ammeter 1 and ammeter 2. So the answer straight away, we solve it even before we read the question. Now, calculate the effective resistance of two light bulb and the 5 ohm resistor. Okay, so remember, 15 ohm is 215 ohm is in parallel. So if you look at the formula, it will be, let's say, if you look at it from basic, okay, the parallel branch is here. So R parallel, if you look at the working, this is R parallel. So if you don't want to do everything in a single straight line, you want to break it up. So I will break down into R parallel. Okay, so the formula for R parallel will be 1 over R parallel equal to 1 over 15 plus 1 over 15, which will be 2 over 15. Remember, this is not the final answer yet. You are supposed to give me R parallel first. So which means you need to inverse this, to inverse here, to inverse here. So it will be 15 over 2 divided, it will be 7.5 ampere. 7.5 ohms. If the parallel branch is 7.5, if it's series, okay, means you just add up you mean your plus 5. Yeah, this is where I get the 7.5 plus 5, answer will be 12.5. So it depends on the working. So some of us, we like to do everything in one step. So you can do R parallel and R series in one step, but take note, okay, of the presentation. If you do the parallel branch, okay, together with the series branch, take note of the presentation. Okay, there is a negative sign. You must indicate the inverse. The inverse is actually represented by this negative sign, -1. Okay, if you're not comfortable with this type of presentation, okay, my advice is actually to break them up. Okay, so what I did was take a look. Okay, find R parallel first. After that, just move on to say R series or R total is actually consists of R5 plus R parallel, because they're in series. So you will get 5 plus 7.5, which actually equal to 12.5. The answer is actually the same. And in fact, I will actually find that my presentation, although it's a bit long, but I would say it's like it's like going back to basic again, looking at the basic formula and work my way out. Okay, I would say it tend to have less confusion about presentation. Do I need to put the -1 there? What does the -1 means in terms of power or these things? So I just like to keep everything back to basic. So even though it's a bit lengthy, but it's actually, I would say it's actually quite clear. Using answer in B and C, the value measured by the voltmeter. So where is the voltmeter first? Okay, so the voltmeter is here. Oh, Okay, the voltmeter is at the battery, so it's what we call the EMF. So the question is asking us about the EMF. Okay, so we want the EMF. So basically, I total, V total, and R total. So if I know the EMF, basically the EMF is actually the V total, or what we call the EMF of the battery. So if it I total, you found already, I total is 1.4. R total is 12.5. So straight away you get the answer. The voltmeter reading will be 17.5. Okay, because the current IT come from the battery. Okay, come from the battery. So IT multiplied by RT will give you the potential difference across the battery. Okay, basic Ohm's law. So, calculate the flow 40 seconds. Okay, calculate the charge flowing through ammeter 2. So where is ammeter 2? Ammeter 2 is here at the 5 ohm. So basically ammeter 2 actually measures where the total current. Okay, so basic formula Q equal IT. Total current at ammeter 2 here is 1.4 amp. Okay, so that's why I have a 1.4 amp here. Okay, time taken is 40 seconds. If you multiply, you work out the math, it will be 56 coulomb. Okay, fairly easy. Okay, so question 6 actually will be quite easy. Question 7, okay, the amount of liquid freezing, okay, 60 degree to negative 22 degree, okay, is being froze, okay, from a liquid 60 degree to negative 22 degree, okay, in the freezing unit, so the numbers are here. Okay, so take note, is a liquid, you start off as a liquid, you freeze. Okay, so this is the temperature. Now describe the arrangement at time 35 minutes. Okay, now take note, when you look at freezing, I will say if this is the temperature graph, this is the time axis. If you look at freezing, if freezing will occur, there will be a stage whereby the temperature actually remains the same. Okay, the temperature remains the same. Okay, so there will be a time whereby the temperature actually remains constant. That particular instances whereby the temperature remain constant, not at the time temperature here. This is what we call your freezing point. Okay, so how do I identify the freezing point? Is whereby there is an instance, there is a timing whereby the temperature remains the same, and that's whereby the object, the liquid is actually freezing from liquid to solid. That's where freezing actually occurs. So based on the question, right, you have to be careful before you answer part A1 first. Although we start off with liquid, it doesn't mean that I want the structure of the substances means in terms of liquid. So you have to see what is the structure at 35 minutes first. Okay, so if you look at temperature, right, you'll find that the temperature actually starts to drop because it's in the freezer. Okay, so when temperature starts to drop, so I say drop. So these three temperature drop actually correspond, these three temperature decrease actually is correspond to this particular line here. Okay, the temperature is getting lower and lower. After that, eventually hit 0, so it will still be yellow. Then what happens is you will notice that actually there is a time interval whereby the temperature remains constant at -10, -10. Okay, now this is the point. This is the section that I have mentioned earlier. This is the section whereby the liquid is actually freezing. It's starting to freeze already at this particular stage. Okay, so actually when you talk about 20 to 30, right, this is where, based on the cooling curve, this is where the freezing is happening. Okay, so this is what we call your freezing. And it occurs at a fixed temperature across a certain timing. That temperature here is called freezing point. And true enough, you look at temperature, it remains constant, -10 degrees Celsius. Then after that, once freezing has completed, it actually starts to freeze down again. It starts to go down again. It starts to become colder. The solid becomes colder and colder. So you take a look, it actually becomes colder and colder, -18, -22. Okay, so this blue color one will correspond to the blue color one on the graph. So when we talk about at 35 seconds, right, when we talk about the molecular structure, we are actually not interested in the liquid structure already. Because at 35 minutes, right, this structure here we are looking at is actually a solid structure. The blue color line here is actually the solid structure already. So when we talk about the structure of solid, Okay, you will be talking about strong intermolecular bonds. You're talking about vibrating about its fixed position. So in terms of structure and in terms of arrangement, it will be actually be vibrating about fixed position. Okay, then it will be vibrating about fixed position. It will be about orderly manner. Okay, so this is how I know what arrangement am I looking at, not by guessing. Okay, it's by deducing. Okay, same thing. 20 to 30 minutes, like I mentioned before, the green color segment, the green color one. This is where freezing occur. Okay, and freezing, what's the description for freezing? Okay, the observable characteristic for freezing is whereby the temperature remain the same. What happens inside the molecules? Okay, what happens inside the molecules is actually the intermolecular bonds are forming up. Okay, you are strengthening the intermolecular bonds. Okay, and that's where freezing occur. Remember, it's the reverse. If I'm melting, okay, I will be actually breaking the intermolecular bonds. Okay, so take note of the various bond breakings or bond forming stages. Part B, okay, we have stove. Okay, we have stove used to heat up the warm water in the kettle. Stove is then after your stove, take note, your stove is shiny, stainless, and steel. Okay, so you have three patterns here. Give me a minute. So you'll be shiny, stainless steel. Okay, sorry, stainless steel. Okay, stainless steel. So same thing as well, the moment you look at convect radiation, you need to know what are the clues that's given. So if you're not sure about the clues or you have forgotten about a clue, okay, I mentioned them before in my lesson. Okay, if I put the link of the video of the lesson in my in the description bar below also for you to take a look if you have forgotten to do a short refresher course. I also insert the a small screenshot of the clues, okay, in the space below. Okay, you can take a look. Okay, if you have forgotten about it, okay, you may want to look at the video again and to do a short refresher course so that you know what are the clues to take note of. Because the clues will actually tell us what are the heat transfer method that is of interest to us. Okay, so for example, shiny, the moment we talk about shiny, okay, we are referring to radiation. Okay, the texture. We're talking about steel, metal, solid, all these things. We are looking at conduction. Okay, so now let's take a look, and after that we look at plastic also. Plastic is also about the material, so it's definitely about conduction. Okay, so it's definitely about conduction. So these are the various clues. These clues actually tell us what method we are focusing on. So that's why when part one, we talk about plastic is used to make handle because it's poor conductor. Okay, so it's poor conductor. So how does it not conduct? How does it not conduct heat as well as a stainless steel? What's the difference? One is metal, one is non-metal. Plastic is what we call non-metal. Non-metal has only one mode of transfer. That is what we call your molecular vibration. If you compare to liquid, if you compare to your free electrons, you compare to your stainless steel, then as for stainless steel, which is metal, you will find that there is actually two modes of conduction. Okay, so we have your molecular vibration, and after that, inside stainless steel, because it's a metal, you also have what we known as the free electrons diffusion. Okay, and these two methods, you'll find that because free electron diffusion are smaller and they actually move much faster, you'll find that the heat transfer via actually free electron diffusion in metal is actually much faster. And as a result, the main mode of heat transfer, main reason why metals are good conductors is primarily because of the existence of your free electron diffusion. So that's why metal is not good, is because plastic does not have free electron. It doesn't allow free electron diffusion to occur. Explain how the process of convection involved in heating. Oh, that's easy. Okay, if heating of the water is a classic question of how convection works. So remember of the keywords. Convection is about the change in density. But change in density, don't just say hot rise, cold sink. Okay, you need to mention the density. Okay, so example, you need to talk about the hot, okay, being able to rise, and because of the density, you must make references to the density, not just hot rise, cold sink. Okay, then after that, the colder water being denser, you actually sink to the bottom side to be heated up. Okay, so you actually it's a two-step process. So, okay, so you look at the keyword. Okay, the keyword when you talk about hot, Okay, the corresponding cold you have to mention. So after that, you talk about the motion, whereby hot water will rise, cold water will sink. Okay, but when you talk about this perspective, you need to mention what is the reason behind it. It's because hot water are able to rise because they are less dense, cold water sink because they are denser. So you look at the corresponding tagging keywords if you look at convection current, not just to explain hot rise, cold sink. And of course, to end it up, it will be the summary to say that the convection current occur or repeated, okay, and convection current is formed. Okay, so you look at in the sense that if you look at the explanation for convection current, it actually consists of 4 sections: the green color one, yellow one, orange, and the dark green. Okay, these are what we call the the keywords that is needed to illustrate the understanding of convection current. And with this, okay, we actually end off with we actually reached the last segment of this particular paper. Okay, so if you have done the paper here, okay, if you have done this paper, okay, do take note of the keywords that when you look at the basics of the basic concept of your N-level paper. Okay, so take note of the gaps. Okay, remember to revise, do your thorough revisions. Okay, take note of the gaps. Okay, and actually after that, remember to do a small reflection of what are the mistakes you have made and what are the ways or what are the possible alternatives, what are the methods that you're going to do to actually cover the gaps to catch up. Okay, if not, okay, same as before, if you need any notifications, remember to subscribe to my channel and actually to press the bell button so that you get notification of any new videos that I upload. Okay, if not, okay, stay hard, study hard, okay, stay safe, okay, make sure you do your revisions, and good luck for your O-level and N-level exam. Okay, bye-bye.